Double fusing refers to the practice of installing fuses or circuit breakers in both the service panel and the branch circuit panel for the same circuit. In general, double fusing is not permitted by the National Electrical Code. However, there is an exception to this rule for elevator feeders. According to NEC Article 620.22b2, double fusing of elevator feeders shall be permitted. The exception for elevator feeders is based on the need for increased safety and reliability in elevator systems. Elevators are used to transport people and must be able to operate safely in the event of a fault. By installing fuses in both the service panel and the elevator machine room, the likelihood of a single fuse failure causing a total loss of power to the elevator is reduced. NEC Article 620.22b2 specifically allows double fusing for elevator feeders. This section states regarding the main disconnecting means that double fusing of elevator feeders shall be permitted. Double fusing is generally not permitted by the NEC. However, an exception is made for elevator feeders, which may be double fused for safety and reliability reasons. The use of double fusing for elevator feeders is specifically allowed in NEC Article 620.22b2. So what does this all mean in practice? Firstly, it is important to understand the general rule regarding overcurrent protection. The National Electrical Code, or NEC, requires that each ungrounded conductor have overcurrent protection at the point where it receives its supply. This overcurrent protection is typically provided by a fuse or circuit breaker. The purpose of overcurrent protection is to protect the conductors from damage caused by excessive current flow, such as in a short circuit or overload condition. Secondly, double fusing, the practice of placing overcurrent devices in series, generally violates this principle. If you have two fuses in series, the fuse with a lower ampacity will trip first. This is desirable and expected. However, it can create coordination issues if the two fuses are not properly sized and coordinated. The primary concern with double fusing is selectivity, also known as coordination. Selectivity ensures that only the overcurrent device closest to the fault opens, minimizing disruption to the rest of the electrical system. Without proper coordination, both fuses might open during a fault, causing unnecessary downtime. However, there is an exception to this general rule for elevator feeders. Let's delve deeper into the reason why. The exception exists because elevators are critical life safety systems. They need to remain operational even in the event of certain electrical faults. The rationale behind allowing double fusing in elevator systems is to enhance the reliability and safety of the elevator's power supply. Now let's talk about the specific requirements in NEC Article 620.22b2. This section allows double fusing, but it also mandates that the fuses be selectively coordinated. This coordination ensures that in the event of a fault, only the fuse closest to the fault will open, while the other fuse remains intact, keeping the elevator running if possible or allowing for a more controlled shutdown. Coordination studies are essential when implementing double fusing. These studies involve analyzing the time current characteristic curves of the fuses to ensure proper selective coordination. The goal is to choose fuses with different tripping characteristics so that the upstream fuse does not trip before the downstream fuse during a fault. The NEC provides guidelines and requirements for overcurrent protection in Article 240. Article 240.1 states that overcurrent protection shall be provided in each ungrounded conductor. Article 240.2 covers the purpose of overcurrent protection, which is to protect conductors and equipment against overcurrent. Article 240.3 provides requirements for the selection and use of overcurrent protective devices. Article 240.4 provides requirements for conductor protection, specifying that conductors shall be protected against overcurrent in accordance with their ampacities. Article 240.6 lists the standard ampere ratings for fuses and inverse time circuit breakers. Article 240.10 covers circuit impedance, short circuit current ratings, and other considerations. Article 240.12 covers the requirements for overcurrent protection coordination. Article 240.21 specifies the location in circuit of overcurrent devices. Article 240.24 covers the accessibility and grouping of overcurrent devices. Article 240.40 covers the disconnection and removal of overcurrent devices. Article 240.60 provides specific requirements for cartridge fuses. Article 240.80 provides specific requirements for circuit breakers. Article 240.81 requires that circuit breakers clearly indicate whether they are in the open or closed position. Article 240.83 provides marking requirements for circuit breakers. Article 240.85 restricts the use of certain circuit breakers based on voltage and current ratings. Article 240.86 covers series ratings for circuit breakers and fuses. Article 240.87 provides requirements for surge protective devices. Article 240.95 covers ground fault protection of equipment. Article 240.100 covers overcurrent protection for feeders. Article 240.101 covers overcurrent protection for branch circuits. Article 240.102 covers overcurrent protection for motor circuits. Article 240.103 covers overcurrent protection for transformer circuits. Article 240.104 covers overcurrent protection for capacitor circuits. Article 240.180 provides specific requirements for overcurrent protection of high voltage systems. Article 240.181 provides specific requirements for overcurrent protection of medium voltage systems. When installing fuses or circuit breakers, it is crucial to select the correct size based on the ampacity of the conductors and the load requirements. Oversizing can lead to inadequate protection, while undersizing can cause nuisance tripping. Always consult the NEC and relevant equipment listings to ensure compliance. Let's break down the implications of double fusing for elevator systems. Double fusing, in this context, involves placing overcurrent protection at both the main distribution panel and the local disconnect in the elevator machine room. The primary benefit is increased redundancy. If one fuse fails, the other should still provide protection, reducing the risk of a complete shutdown. Now, let's talk about the challenges associated with double fusing. As mentioned earlier, coordination is critical. Without proper coordination, a fault could cause both fuses to trip, defeating the purpose of the redundancy. Coordination studies require a detailed analysis of the elevator system's electrical characteristics, including fault current levels and fuse time current curves. In these studies, the goal is to select fuses that trip selectively, ensuring that the fuse closest to the fault clears the fault while the other fuse remains unaffected. Additionally, regular maintenance and testing of the overcurrent devices are essential to ensure they function as intended. This includes verifying the fuse ratings, checking for signs of overheating or damage, and testing the tripping characteristics of the circuit breakers. Double fusing is permitted in elevator systems under very specific conditions, primarily to enhance safety and reliability. However, it requires careful design coordination and maintenance to ensure it functions effectively and does not create additional hazards. Remember, always consult the latest edition of the NEC and qualified electrical professionals for specific guidance on elevator electrical systems and overcurrent protection. In summary, the allowance for double fusing elevator feeders under NEC Article 620.22b2 stems from the critical need for uninterrupted and safe elevator operation. This exception, however, is contingent upon adherence to stringent coordination and selective tripping principles. The purpose is to ensure that in the event of a fault, the overcurrent protective device closest to the fault activates, isolating the issue while maintaining power to the rest of the system, thereby enhancing both safety and operational reliability. Let's consider the practical implications. Imagine a scenario where an elevator motor develops a short circuit. In a standard electrical system, a single fuse or circuit breaker would trip, cutting off power to the motor and halting the elevator. Now envision the same scenario in a double-fused elevator feeder system. If the fuses are properly coordinated, only the fuse located in the elevator machine room closest to the motor would trip. The upstream fuse in the main distribution panel would remain intact, ensuring that other essential systems in the building continue to operate without interruption. This selective tripping is crucial in minimizing downtime and maintaining the overall safety of the building's electrical infrastructure. However, achieving this level of coordination requires careful planning and expertise. Electrical engineers must conduct thorough coordination studies, analyzing the characteristics of the entire electrical system to determine the appropriate fuse sizes and types. These studies take into account various factors, including the available fault current, the impedance of the conductors, and the time current curves of the fuses. Furthermore, regular maintenance and testing are essential to ensure that the overcurrent devices continue to function as intended over time. This includes periodic inspections, testing of tripping times, and replacement of any damaged or worn components. In addition to the technical aspects, it is also important to consider the regulatory requirements. Electrical inspectors will scrutinize elevator feeder systems to ensure compliance with the NEC and other applicable codes. Therefore, it is imperative to maintain accurate documentation of the coordination studies, fuse selection, and maintenance records. Moreover, elevator technicians and maintenance personnel must be properly trained to understand the intricacies of double fuse systems and to perform routine inspections and troubleshooting. This requires ongoing education and certification to ensure that they possess the necessary skills and knowledge. The complexity of double-fused elevator feeder systems underscores the importance of engaging qualified professionals for design, installation, and maintenance. Attempting to implement such systems without proper expertise can lead to safety hazards, code violations, and operational inefficiencies. In addition to the increased safety and reliability, double fusing can also offer other benefits. For example, it can provide enhanced protection against transient overvoltages and surges, which are common in electrical systems. By using appropriately rated fuses, it is possible to mitigate the impact of these disturbances and prevent damage to sensitive equipment. Furthermore, double fusing can facilitate easier troubleshooting and maintenance. By having overcurrent devices at both the main distribution panel and the elevator machine room, technicians can quickly isolate faults and perform repairs without having to shut down the entire building's electrical system. However, it is important to note that double fusing is not a panacea. It is not a substitute for proper design, installation, and maintenance practices. In fact, if implemented improperly, it can actually increase the risk of electrical hazards. For example, if the fuses are not properly coordinated, it is possible for both fuses to trip during a fault, leaving the elevator without any overcurrent protection. Therefore, it is essential to approach double fusing with caution and to carefully consider all of the potential implications before implementing it. Remember to consult with qualified electrical professionals to ensure that the system is designed and installed in accordance with all applicable codes and standards. Always prioritize safety and reliability over cost savings or convenience. Electrical systems are complex and potentially dangerous, and it is essential to take all necessary precautions to protect people and property. Double fusing, while permitted under certain circumstances, should be approached with a thorough understanding of its potential benefits and risks. And when in doubt, always seek the guidance of a qualified electrical professional. Proper coordination and maintenance of overcurrent devices are paramount in ensuring the safety and reliability of electrical systems. Double fusing, as permitted for elevator feeders under specific NEC guidelines, should be implemented with meticulous attention to detail, ensuring that it enhances, rather than compromises, the overall performance and safety of the electrical infrastructure. The goal is to minimize disruption and maximize the safety of the elevator system and the building as a whole.